While going through the paper, I found this problem really interesting. We will see how. But first, let me tell you what is happening in this case. So a particle is moving with a velocity v0 and it collides head-on with another identical particle which is at rest. Now what happens is that the final kinetic energy of the particles is 50% more than their initial kinetic energy. And with this given information, you have to find out the magnitude of the relative velocity of these particles after the collision. That is, the magnitude of the velocity of separation. So the concepts involved in this case are collision and momentum conservation. And the level of difficulty, I would say, is medium. Now, what kind of collision do you think this is? Is it perfectly elastic collision, perfectly inelastic collision, or something in between? Well, recall that in the case of perfectly elastic collision, the initial kinetic energy was equal to the final kinetic energy of the particles, right? And the coefficient of restitution E was 1. But here the final kinetic energy is more than their initial kinetic energy. Well, how? Well, one of the possibility that I can think of is that when the particles come in contact during collision, some chemical reaction happens, due to which the chemical energy gets converted into kinetic energy. And that's how the final kinetic energy is more than their initial kinetic energy. So what I'm going to do is solve this problem via two methods. One is going to be a longer method and the other one is going to be a shortcut. So let's see method number 1. Let's assume this particle is moving with a velocity v0 and the mass is m, and the other particle which is kept at rest is this one. And let's assume that after the collision, the first particle is moving with the velocity v1 and the second one is moving with a velocity v2. And what do you have to do? You simply have to find out what is v2 minus v1 in terms of v0. So basically this is the problem. So first let's conserve the linear momentum of the system. Before collision, the linear momentum is mv0, and after collision the linear momentum is mv1 plus mv2. From here we get one equation, v1 plus v2 is equal to v0. And as mentioned in the problem statement, the final kinetic energy of the particles, that is mv1 square, half mv1 square plus half mv2 square, is 3 by 2 of the initial kinetic energy, that is half mv0 square into 3 by 2. Right? So this should not be whole square but just half mv0 square. And now what we can do is cancel half and m from both the sides. We have one more equation, which is v1 square plus v2 square is equal to 3 by 2 v0 square. Now let's write it like this. v1 plus v2 whole square minus 2 v1 v2 is equal to 3 by 2 v0 square. And why we are doing this? Because we already know the value of v1 plus v2. So this is going to become minus 2 v1 v2 is equal to 3 by 2 v0 square minus v0 square, right? That is 1 by 2 v0 square. So we have the value of 2 v1 v2 from here to be equal to minus v0 square by 2, right? And now what we can do is apply the formula V2 minus V1 whole square. And how we are going to apply it? Look on your screen. We are going to do it like this. So V2 minus V1 whole square, I can write this as V1 plus V2 whole square minus 4V1 V2, right? Now V1 plus V2 is V0, so this is V0 square, and 2V1 V2 is minus V0 square by 2. This makes 4V1 V2 to be equal to minus V0 square. So minus minus will be plus, and this is 2V0 square, and from here V2 minus V1 is going to be equal to under root of this, that is V0 root 2, right? So the magnitude of the velocity of separation V2 minus V1 is going to be equal to root 2 V0. And now the shortcut. Well, as I told you in the beginning, in this case E is greater than 1, right? And the definition of coefficient of restitution is the ratio of velocity of separation to velocity of approach. So in this case, can you see that the velocity of separation is V2 minus V1 and velocity of approach is V0 minus 0, and this should be greater than 1. This means that V2 minus V1 should be greater than V0 for this to happen. And can you see that in only one option this is satisfied? Because in option A, the velocity of separation is less than V0. In option C also it is less than V0. And option D also it is less than V0. Which leaves us with option B as the right answer. So you could have saved a lot of time if you could have approached this problem via the shortcut. So in this case, we can tick option B as the right option. So there are 7 identical discs, each of mass m and radius r, and they are welded in the arrangement as you can see in this figure. You have to find out the moment of inertia of this system about an axis perpendicular to the plane and passing through the point P. Okay? So the concepts on which this question is based are moment of inertia of the disk and the parallel axis theorem. And the level of difficulty is kept as medium. But this question is going to become really hard for you if you try to find out the moment of inertia of each disk individually and then plan to find out the total moment of inertia. So we are not going to follow this approach. But what we are going to do is find out the moment of inertia of this system about an axis perpendicular to the plane and passing through the point O, which you can see is also the center of mass of this system. And then we will apply the parallel axis theorem to find out the moment of inertia about the axis passing through the point P. Okay? So first let's find out the moment of inertia of the central disk. In this case, the axis of rotation becomes its natural axis of rotation, right? And the moment of inertia of this one about this axis is going to be mr square by 2. Let me remind you that the axis is perpendicular to the plane and passing through the point O. And let's find out the moment of inertia of any one of these 6 disks. Okay? Let's focus on this one. Because we know by symmetry, the moment of inertia of the other 5 is going to be the same, right? So for this one, the moment of inertia about an axis passing through its center and perpendicular to the plane is going to be mr square by 2, and the distance is 2r. So the moment of inertia about the axis passing through O is going to be mr square by 2 plus m into 2r whole square, right? And this is going to be mr square by 2 plus 4mr square, that is 9mr square by 2. And now to find out the moment of inertia of the 6 disks, we can multiply this factor with 6. So this will become plus 54 mr square by 2. And the moment of inertia of the system about the axis passing through O and perpendicular to the plane is going to be 55 mr square by 2. So far so good, right? And now we are going to apply the parallel axis theorem. So the total mass of the system is 7m. And to find out the moment of inertia about the axis perpendicular to the plane and passing through the point P, we can add IO, which is 55 mr square by 2 to 7m into, and can you see that this distance is 3r, so 9r square, right? So this factor is 63. So we can add 63 mr square to this one to find out the final answer. So this is going to become 55 plus 126 mr square by 2, that is 181 mr square by 2. So in this case, the correct option is option D. 2 questions back to back on moment of inertia. Well, that's interesting. Anyway, in the mentioned case, you can see that the whole disk of radius r has a mass 9m. Now what happens is that a circular portion of radius r by 3 is removed like that. You have to find out the moment of inertia of this about an axis perpendicular to the plane and passing through the point O. So the mapped concepts remain the same: moment of inertia of the disk and parallel axis theorem. And this question is easy. So what's the drill? Well, the drill is that we will find out the moment of inertia of the whole disk, and then we will subtract the moment of inertia of the removed portion. But remember that the axis of rotation should remain the same, which is perpendicular to the plane and passing through the point O. Okay? So finding out the moment of inertia of the whole disk without the portion removed is 9mr square by 2, right? So this is the moment of inertia of the whole disk about the axis of rotation. And now let's find out the moment of inertia of the removed portion about the same axis of rotation. For that, first we will have to find out what is the mass of this removed portion. Well, the mass is uniformly distributed, and in the area pi r square, the mass contained is 9m. And can you see that the area of the removed portion is pi r square by 9, which makes the mass of the removed portion to be equal to 9m by 9, that is m. And now first we will have to find out the moment of inertia of the removed portion about the axis perpendicular to the plane and passing through its center. So the moment of inertia about this axis of the removed portion, which is in the form of the circular disk itself, is going to be 1 by 2 m r square, and radius in this case is r by 3, so this is going to be r square by 9, right? So mr square by 18 is the axis of is the moment of inertia of the removed portion about its natural axis of rotation. And now we can use the parallel axis theorem plus m 2r by 3 square, right? And this is the moment of inertia of the removed portion about the axis perpendicular to the plane and passing through the point O. So this becomes, so this is nothing but 4 by 9. So mr square by 18 plus 4 by 9 mr square gives us 9 mr square in the numerator, and this is mr square by 2, right? And now what we will do to find out the moment of inertia of the given case, we have to subtract mr square by 2 from 9 mr square by 2. Minus mr square by 2 comes out to be 4 mr square. And this is the moment of inertia of the disk with the removed portion. So you can take option A as the right option in this case. So a particle is moving in a circular orbit of radius r with uniform speed. The centripetal force acting on the particle is inversely proportional to r raised to the power n. You have to tell how time period of rotation depends upon r. So the concepts on which this problem is based are uniform circular motion and centripetal force. And this problem is pretty easy. So let's start solving. In this case, it is given that F is inversely proportional to r raised to the power n. Let's assume that the centripetal force is equal to some constant divided by r raised to the power n. And if this is a centripetal force, then you know this is going to be equal to mv square by r, where m is the mass of the particle, v is its speed, which remains constant, and r obviously is the radius of the circular orbit. Now can you see from here, v is proportional to 1 upon r raised to the power n minus 1 divided by 2, right? So m is a constant and v is also a constant. And we know that the time period is going to be equal to the circumference of the circle, 2 pi r divided by speed. And from here we can find that the time period is proportional to r raised to the power n plus 1 divided by 2, right? Because v varies with r like that. So we have the final answer in this case. T is going to be directly proportional to r raised to the power n plus 1 divided by 2, and option C is going to be the right option. In this simple case, a parallel plate capacitor containing a dielectric is connected to a battery. You simply have to find out what is the induced charge that is residing on the dielectric. So easy problem, right? Concepts are dielectric induced charge and the level is easy. You have to choose the right option from these given options. So you know that with the introduction of the dielectric, the capacitance of the parallel plate capacitor will increase by the factor K. So the new capacitance is going to become K times the old capacitance. And the charge or the magnitude of charge on each plate of the capacitor is going to be, so we know that Q is CV, right? So charge on each plate is going to be KC naught into V. Yeah? So let's find out what is the magnitude of the charge on the plate of the capacitor. So the value of K is 5 by 3. So 5 by 3 into 90 picofarad, that is 90 into 10 raised to the power minus 12 into 20 coulomb is the magnitude of the charge. And we know that the induced charge is Q1 minus 1 by K. Simple formula. So when you apply this, the induced charge is going to be equal to 5 by 3 into 90 into 10 raised to the power minus 12 into 21 minus, and this is 3 by 5, right? And when you simplify this, you are going to get the induced charge on the dielectric to be equal to 1.2 nanocoulomb. So, in this case, option A is going to be the right answer. So, the source EMF and the current in an AC circuit depend upon time, like this. You have to find out the average power consumed by the circuit in each cycle and the value of the wattless current in the circuit. So an easy problem. Can you see from the equation that the current is lagging behind the applied EMF by a phase factor of pi by 4? So in this case, the value of phi is pi by 4. And we know that the average power consumed is ERMS, IRMS cos of phi. Let's quickly apply this. So the average power consumed by the circuit is going to be equal to ERMS, that is going to be E naught by root 2 into IRMS, which is I naught by root 2 into cos of 45 degree, and this gives me 1000 by root 2 watt as the average power consumed in each cycle. Now, how will you find out the wattless current in the circuit? Let's see the phase diagram. In the phase diagram, the current lags behind by a phase factor of pi by 4. And can you see that the component of the current which has the phase factor pi by 2 with the applied EMF is going to be the wattless current. Just like in the case of purely capacitive circuit or purely inductive circuit. So we have the value of the wattless current in the circuit to be equal to IRMS sine of phi. And can you see this comes out to be 20 by root 2 into 1 by root 2, that is 10 ampere. So we have the answer in this case. You can see that option B is the right option. The combination of two batteries in parallel is connected to a load resistor. You simply have to find out the potential difference across the resistor. So a simple problem based on current electricity where the level of difficulty is easy. So you can go about this via two methods. The first method is using Kirchhoff's loop rule to find out the potential difference. You can assume some current to be coming out of this battery, some current to be coming out of this, and then apply the loop rule to solve for the potential difference, which is going to be I into R. But I am going to apply method number 2, where I am going to replace these two batteries with a single one. Okay? So let me write the formula that we are going to use. The equivalent resistance of the equivalent battery is going to be R1 R2 divided by R1 plus R2, where the value of R1 is 2 ohm and R2 is 1 ohm. And then you can use E equivalent by R equivalent. You know the formula. E1 by R1 plus E2 by R2 to find out the equivalent EMF of the equivalent battery. And then it is very easy. Once you have this, you can find out the current in the circuit, right? And once you have the current, you can find out the potential difference across this resistor by applying V is equal to I into R. So when you solve for this, then you are going to get the value of the potential difference across the load resistor to be equal to 11.56. I trust your calculations and hopefully you will get the desired answer. So you can see in this case option B is going to be the right option.